Having looked at addition and subtraction cryptarithms, let's now turn our attention to multiplication cryptarithms. So here is a multiplication cryptarithm. A two-digit number AB is multiplied by a single-digit number C, and their product is the three-digit number AAA. We need to reconstruct the original digits in this multiplication exercise from which this encoded version was built. So let's go over the multiplication steps required to obtain this product to see if we can get any clues from that. When the digit C was multiplied by the digit B, in the units place we obtained the digit A, which was different from both B and C, and possibly there was some carry from this multiplication operation. And when this digit C was multiplied by the digit A, and when the carry from the previous operation was added to that result, what was obtained was a two-digit number AA. That's how we got this three-digit number as the result of this multiplication. Now if we just look at these steps that I just discussed, it's not clear from the steps what the values of A, B and C, what digits A, B and C really represent. For example, I can think of many possible values for C and B such that their product would have a third digit A in the units place. So there'll be many different combinations. For example, C could be 2, B could be 3 and A could be 6. Or C could be 7, B could be 9 and A could be 3, because 7 times 9 is 63. So it would be pretty inefficient to look at all possible combinations of values for A, B and C. So we need some better way to proceed. Now we have 6 letters in this problem: 1, 2, 3, 4, 5 and 6, and 4 of those letters are A. So if we want to look at the different possible values that these digits can take, it makes sense to start with A, because for a given value of A, if we fix a particular value for A, say A is 1, if we put A is equal to 1, then 4 of these letters can be replaced by 1, and hopefully we should be able to figure out what the other two letters are in that case. So at the outset, before we start analyzing this, what are the possible values that A can take? Can A be 0? No, because it doesn't make sense to have 0, 0, 0 as a number, at least not in the way we are representing numbers here. And we can't have an A, we can't have a 0 in the leading position for any number. So A cannot be 0. So let's see whether A can be 1. Can A be a 1? Well, let's try putting A equal to 1 and see if we get legitimate values for the letters B and C. So if A is 1, we have 1B that's being multiplied by C, and the result is 111. Are there any digits B and C? Are there any different digits B and C such that the number 1B when multiplied by C produces 111 as the result for their product? Well, let's try to factorize this number 111 and see if any of the factors can be mapped to numbers with this particular format. So 111 can be expressed as the product of 3 and 37. If you are familiar with tests of divisibility, you can see that 111 would be divisible by 3 because the sum of the digits in 111, 1 plus 1 plus 1, is 3. And if the sum of the digits is divisible by 3, then the number itself is divisible by 3. So 111 can be written as 3 times some number, and if you can calculate what that number would be. by dividing 111 by 3 using long division, and you would get 37 as the quotient if you did that. And 37 and 3 are both prime numbers. Since they are both prime numbers, they cannot be split further as the products of smaller numbers. They cannot be expressed as the product of two smaller numbers. So these are the only two factors of 111 apart from 1 and the number 111 itself. So we are interested only in these kinds of factors. So if 111 can be expressed only as 37 times 3, it's clear that it cannot be expressed as a number 1b times another number c, because the only two-digit factor that this number has is 37, which has a 3 in the tens place, not a 1. So can a be 1? The answer is no. A cannot be a 1. Now can a be 2? Let's see what happens if we replace the letter A with 2. We get 2b times c being equal to 222. So this is the product of multiplying these two numbers. Now let's see if 222 can be written as the product of two numbers, where one of the numbers is a single digit number and the other number is a two-digit number with 2 appearing in the tens place. Now 222, if we try to factorize 222, we can just reuse the fact that we have already factorized 111, because 222 is nothing but twice of 111, and since we know that 111 can be factorized as 3 times 37, we can factorize 222 as 2 times 3 times 37. Now if you look at these factors, if you look at these prime factors of 222, do you find any way to construct a factor of 222 which has a 2 in the tens place? Well, there is no such factor possible, because 37 begins with a 3, and anything that is multiplied by 37 will obviously be larger than 29, which is the largest possible number that can match this format. And 2 times 3 is 6, and 6 is certainly smaller than 20, which is the smallest possible number which can match this format. So it doesn't look like we can choose one or more of these factors to form a number between 20 and 29, which is what we are looking for. So 222 therefore cannot be expressed as the product of two numbers where one of the two numbers is between 20 and 29. So can A be 2? No. Let's see if A can be equal to 3. Well, what happens if we put A as 3? In that case, some number 3b times some single digit number c should be equal to 333. So again we need to check whether this number 333 can be factorized in a way that it allows us to express 333 as the product of two numbers, the first of which is a two-digit number with 3 in the tens place. So first let's factorize 333 into its prime factors. 333 can be expressed as 3 times 111, and we know that 111 has two factors, 3 and 37, apart from 1 and the number itself. So we can express 333 as 3 times 37. Now we need to figure out whether 333 can be expressed as the product of two numbers where one of the numbers is a two-digit number that begins with a 3. If you look at this prime factorization of 333, you can see that there is a two-digit number which is a factor of 333, and that's 37. So it's possible to it's possible that this number 3b could be 37. So let's say that we choose b as 7. In that case, 3b would be 37. Now, can we get a legitimate value for this digit c? Well, if 3b is 37, then c is whatever number it needs to be multiplied with to get 333. So 37 needs to be multiplied by 3 times 3, or 9, in order to get 333. And since 9 is a single digit number, we can actually make c as 9, and in that case we would actually have obtained legitimate values for all three letters A, B and C, which satisfies the original encoded version. So that means 37 times 9, which if you carry out this multiplication is 333, is a valid solution to the cryptarithm. A is 3, B is 7 and C is 9. Now, even though most cryptarithms have only one solution, we should verify that there are no other solutions to this cryptarithm. So we do need to go through all possible values for A rather than just stop here because we found one solution. So let's see if A can be 4. Can A be 4? If A was 4, then we want to choose values for B and C such that the number 4B times C would yield the product 444. Now, like as before, we can express 444 as 4 times 111. We can write 4 as 2 times 2. These would be the prime factors of 4. And as before, we can write 111 as 3 times 37. Now, can we choose one or more of these prime factors and construct a two-digit number which starts with a 4 as one of the and make that as one of the factors of 444 over here? Well, if we take 37 and if we multiply it with 2, we are going to get 74. 74 is much larger than 49, which is the maximum possible value that this particular number can be. So clearly multiplying 37 with any other number is not going to yield this kind of a number. What if we multiply all the other numbers? 2 times 2 times 3, which is 4 times 3 would be 12. But 12 is still smaller than the smallest possible number that can have this format, which is 40. So it doesn't look like we can split 444 into two numbers whose product is 444 and whose format is 4b and c. So A cannot be a 4, and we've seen that it cannot be a 3 as well.